Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation. And in particular, we will continue to unpack the photoelectric effect. So, last time we introduced the idea of the photoelectric effect, and we described it as the emission of electrons when a material is exposed to electromagnetic radiation. Those electrons are known as photoelectrons. The material is usually a metal, and the radiation involved is usually IR, optical, or UV radiation. This is the photoelectric effect, but the experiment conducted to sort of measure different properties of those photoelectrons is a sight more complicated, okay? And it looks like this, and we're going to go through it. So here we have a light source. That light source is shining, UV, optical, or infrared light on what is called the metallic photosurface. So this is the surface from which the electrons will be emitted. Those electrons are emitted from the photosurface. So all of the photoelectric effect is happening right there. But we have a setup designed to sort of measure those properties. So let's take a look at it. After the EM radiation is shown at the metallic surface, the emitted photoelectrons contact the second plate. So there's a second electrode right here. And they're detected as the photocurrent. That is, they are detected by this ammeter here measuring the tiny current passing through this due to those incoming photoelectrons. And that current is known as the photocurrent. Note, it is just a normal current, but it's caused by the fact these electrons are striking this particular plate. That current is measured by the ammeter. Then we have a sort of battery setup or power supply setup so that the experimenter can apply an external potential difference to this setup. And I'll explain why in a bit. The voltmeter measures that particular potential difference. But the external potential difference can be applied in two ways. In the first, the experimenter could set up an external potential difference so that this particular electrode was at a high potential difference. That is, it was attracting these emitted electrons and thereby sort of accelerate those electrons until they hit this particular electrode and are measured as the photocurrent right here. And sometimes we'll talk about sort of why you might do that. And it can be increased, and that is one of the ways to sort of hook up this applied potential difference. But more importantly and more commonly, you'll have it hooked up the other way so that the applied potential difference is slowing down the electrons. So you apply a potential difference so that this particular electrode is kept at a low potential and therefore is going to repel these electrons. And in particular, you can adjust this potential difference until just at the point when the current going through this ammeter drops exactly to zero. Okay? This applied potential difference has a technical term, and it is known as the stopping voltage. So here's what's going on. These electrons are emitted, and they have a range of kinetic energies. Or I should be a little bit careful. They're emitted in a range of directions with particular velocities, okay? Some of them are a little bit up, some of them are a little bit down, but the ones that are going to reach the plate the most, okay, so that require the most energy to slow them down, are the ones that are ejected sort of head-on. We'll call these the maximum kinetic energy electrons. Other electrons that are emitted in this direction may have the same amount of kinetic energy, but they won't have the same horizontal velocity here. And for the ones that are ejected exactly out of the photosurface at the other electrode, the stopping voltage is the potential difference you need to apply to get them just barely to slow down and turn around right here before contacting the second electrode and being detected as the photocurrent. That particular value of potential difference you need to apply is known as the stopping voltage, which will be discussed in the next video in more detail. And why is this important? This is important because the exact value of the stopping voltage, Vs, allows you to measure the maximum kinetic energy of those photoelectrons after emission. So we can measure the maximum kinetic energy that these electrons have, and that will tell us a lot about what is going on, as it turns out.